You see the first page on your note, and after removing your earbuds and making sure you understand that this is an enjoyable process of learning new things, and we should be welcoming it rather than messing around during the lesson, let's keep our minds open. And after seeing the first page and looking at the situation and being intimidated, a lot of people shut down. Okay? A lot of people are like, yo, I'm keeping my earbuds in. Yo, I'm going to ask you to go to the bathroom during this lesson. Yo, I'm just going to copy down and check out. Because it looks like it's something new and something intimidating. Everybody hates physics class. Nobody likes physics. But I'm about to tell you that what we're going to learn, we've already learned. That this lesson today is essentially review. Okay? The questions and the things you're going to be doing, you already know how to do. With one big difference, it looks different. It looks different. Okay? Now, here's the key. All units, Unit 7, all units, and I used to like incorporate this throughout the first semester, but I've changed it. We're just focusing on this one thing all unit, and that is a dude who moves on a line. You guys see this? So that's every single situation. This unit is the dude is moving on a line. The entire unit is a dude moving on a line. But you're going to tell me like, oh, when is the dude furthest left? Oh, when is the dude furthest right? When does the dude change directions? When does he go from over there to there? Is he going towards the origin? Is he going away for the origin? Okay, we're going to have to answer all these questions. But it turns out we've already answered those. You already know how to do these things. And all the while, time is passing. So as time is passing, where is our dude? How is he moving? Is he speeding up? Is he slowing down? Where is his location relative to the origin? This is the stuff we're going to figure out. Here's my dude. Perfect. My dude is positioned right now, and I just paused. I just paused the stopwatch. This is important to know. Time is passing, but you can pause. So at the moment that the clock stopped at 13 seconds, this is time. This is always what's going to be occurring. Time. The dude has a position. So I would say my dude's position is -2 at time t equals 13. We're going to call this position a position on an x-axis. So I could say, here's my dude right here. And here is a new function, an x of t function. This is a position function. This is a location at a specific time. Okay? Position means location. And my position of this dude at time 13 is -2. X of 13 equals -2 means my dude is positioned at the meter mark of -2, 2 meters to the left of the origin, when the stopwatch reads 13 seconds at that moment in time. Cool? Cool. Now, you're used to this -2 being like a y coordinate. No, don't worry about it. Don't think about it that way anymore. This -2 is a location. Keep in your brain, the dude is on an x-axis. So he's at a location. Don't think about things two-dimensionally. Great. Maybe my dude started at this position of 2 and moved around a bunch like I showed you and then at the 13th second ended up being here? Well, I could say my starting position, my position at time 0, was 2. Cool? Cool. Well, what happened in between? Well, we saw the dude could move to the left. He could move to the right. Well, what's going on in terms of his position? Well, his position could be increasing from 2 to 3 to 4 to 5 to 6 to 7 to 8. Could keep going. Or your position could be decreasing from 2 to 1 to 0 to -1 to -2 to -3 to -4 to -5 to -6. Cool? You guys good with that? All right, so direction is important. Here, the dude is traveling to the left, but while that's happening, position, or x of t, is decreasing. Right? From 2 to 1 to 0 to -1 to -2 to -3. Here is a situation where the dude is traveling to the right. If you are traveling to the right, your position values are increasing. Okay, cool. Great. Don't see the calculus yet, Mr. Metzner, but I'm going to trust you. Kind of understand the situation, a dude moving on a line. All right, so let's make a connection. Ready? You're going to kind of make the connection yourself. It's going to be very obvious for you guys to do. Let's say at t equals 0, the dude is located at a position of -3. Could you write that out in terms of x of t? X of t being position, write out that the dude started at -3. Let's go ahead and write that next to t equals 0. Hopefully you're writing x of 0 is -3. At a time of 0, the dude is located at a meter mark at a position of -3. It appears that his position's increasing or he's moving to the right. After 2 seconds, the dude is now at a position of 5. He's 5 units to the right of the origin. This is the origin. Origin is our starting, not a starting point, it's just a 0 position. We don't always start at the origin. I started at a position of 2 in the previous one. Okay? So, dude eventually moves past the origin. He gets to a position of 5. Okay, tell your neighbors. What happened? What can you say? Go ahead, make a statement. Be specific. Give me some numbers. Okay. Many of you are like, well, he moved to the right 8 meters over the course of 2 seconds. Some of you went a little further and said, well, 8 meters over the course of 2 seconds was 4 meters per second. We'll just go with it. Some of you, most of you did not think about how you did those calculations. You did not think that you did 5 minus -3, 2 minus 0. You did not think about taking a final position and subtracting an initial position and subtracting a final time versus an initial time. You did not realize that your calculations were the calculations of what that we use often in this class. It's an S word, slope. Okay? So you didn't realize that what you did was found the slope of position. And when you realize you find the slope of position, you realize that slopes are rates of change. And the rates of change of position gave you what you guys have known to be a velocity. Now, this is an average velocity. 4 meters per second on average. You don't know that he was traveling 4 meters per second. You didn't know he was traveling consistently to the right. He could have done a lot of stuff in between those times. But on average, he traveled 4 meters per second to get from a position of -3 to a position of 5. Okay. Well, if slopes of positions give us velocity, and if the average rate of change, which is the slope of the secant, I'll put that on the other side. If the average rate of change of position, which gave you the slope of a secant of a position graph, gives you an average velocity, then the slope of a tangent of position must give you an exact velocity, right? Which means the instant rate of change of position, which gives you the slope of the tangent of position, which gives you the exact velocity, must be the case. Or, one more word that I've not thrown out there, what is another word for instantaneous rate of change? What is another word for slope of a tangent that we've used all year? I have tangent. I have instantaneous rate of change, synonymous with derivative. And here's the key. Thank you, Murdoch. Just making sure everybody got it. Ready? You haven't known this the entire time you took physics. The derivative of position is velocity. You haven't known this the entire time you took physics. The slopes of position, the rates of change of positions are velocity. I'm trying to make you see that what you're going to be doing, which looks different, is actually the same stuff we've already done. We're going to be reviewing. And I know you don't believe me. And you're just like, I don't see it, Mr. Metzner. I'm going to check out. I'm going to use the bathroom really soon. I guarantee you. I'm going to have to use the bathroom right when I have to think. Are you familiar with these equations? These are equations that you were given in physics. You were given these equations for projectile motion, where it's like we got gravity is A, we got an initial velocity, it's a number, we got an initial position, and that gave me the position, x of t. And then you're given, oh, your velocities, or your initial velocity plus like the acceleration under gravity. Watch this. Let's take the derivative of this equation. Okay? Now, we are using t's instead of x's in this unit. It's not y equals x's. It's like positions or velocities of t's. Okay? So like positions equal t's kind of thing. So let's start with like this initial position. Let's pretend our initial position is 5. What's the derivative of that? What's the derivative of 5? 0. Good. Okay. Now, we have an initial velocity. Let's pretend it's 6. 6 times t. Now, we don't have to do anything special, guys. The derivative of 6t is what you're used to being like the derivative of 6x. So what's the derivative of 6t? 6. Okay, well, 6 is replacing v sub I, so here's v sub I. Let's pretend this is like -9. We can even pretend it's -9.8. So we have -9 t squared. What would be the derivative of -9 t squared? Tell your neighbors. What's the derivative of -9 t squared? Yeah, the 2 comes down, the 2's go away, and you have negative 9t. Well, that's a times t. What do you notice? We just created this, but by taking a derivative. You didn't see it because you didn't know about the derivative rules when you took physics. But if you take the derivative of that, you get that. If you take the derivative of this, you get that. It was right there in front of you. You just didn't see it. Okay, let's keep going. Let's say my dude is speeding up. It's not just about constant motion left and right. We know about the idea of acceleration. And it's like, oh, the dude could speed up. And he could be going faster in a direction. And faster in another direction. Okay? So, let's pretend the dude started with a velocity of 1 meters per second. By the time he got to the position of 5, he's got a velocity of 11 meters per second, and this is over the course of 2 seconds. Well, you could probably talk to me about the change in his velocity. Okay? He increased his velocity 10 meters per second over the course of 2 seconds. Right? You're talking about how things are changing. That would be 5 meters per second per second. Don't like saying that. Well, seconds divided by seconds become seconds squared. It's really seconds times seconds becomes seconds squared. Meters per second divided by seconds becomes meters per second squared. Cool. And the way you got that 5 was you took 11 and you subtracted 1. You took 2 and you subtracted 0. You took our final velocity minus our initial velocity over the change in your time. You found a slope of velocity. Slopes give you the average rate of change of velocity, and the average rate of change of velocity gave you what you guys consider to be an acceleration. Okay, meters per second squared, speeding up, slowing down. Well, if the slope of velocity is an acceleration, and if the slope of a secant of velocity is an acceleration, what else can we say? Anybody? Tell your neighbors. Shout out to your neighbors. If slopes of velocity are acceleration, what can you say that makes sense in this class, this calculus class? Yeah, well, the instantaneous rate of change of v, which gives you the slope of the tangent of v, would give you your exact a. What is one thing that means instantaneous rate of change, which means slope of a tangent? The derivative of v has been a all along. Wow, this is incredible. So you're telling me in physics, when we talked about motion, that the entire time we talked about motion, we are talking about derivatives. You were told x's derivative, which you didn't know about, but now you know, x's derivative is v. V's derivative is a. Can you do one more thing for me to tie it all together? If x's derivative is v, and v's derivative is a, keep going. What else do you know? Sure, a's antiderivative is v. Cool. Okay. If x's derivative is v, v's derivative is a, what else? Danger, what'd you say? A second derivative of x is a. You guys have been used to f, f prime, and f double prime in this class. Well, let's introduce ourselves as x prime, which equals v, and x double prime, which happens to be v prime, which happens to be a. Motion is just a first derivative and a second derivative, and an original function. The questions you're going to be asked, which deals with like how quickly things are moving. You're going to be thinking, oh, I need all these formulas. I need all this new stuff. This is going to be crazy. But it's not. Nothing's going to be new to you. You just need to know that v's been a derivative all along. And a has been a second derivative. You will need to know how these signs, being positive or negative, is actually just like a derivative of x's signs being positive and negative. If x prime is positive, what's that tell you about x? If x prime is negative, what's that tell you about x? Fill out the chart. X must be increasing then decreasing. If position's increasing, we talk about going right. If position's decreasing, we talk about going left. If we analyze signs of A, what we'll realize is that it's the same as V prime, which will tell us about V increasing or decreasing. It could tell us about X's concavity, but when it comes to motion, let's not worry about concavity, okay? It'll have to do with speeding up and slowing down, which we will talk about later. But motion is only motion, and your physics class in motion is really just an F and F prime and an F double prime. Okay? And it goes the other way. You want to go from A to V, take the antiderivative. You want to go from V to X, take the antiderivative. Do you want to take the antiderivative of X? Like doesn't really make sense to you, but you will see in the future there is one application where we want to go past X to big X or go past F to big F. Like we talked about last class, like why would we want big F? It's like, don't worry about it right now. But we'll use it later in this unit. Cool? All right, so here we go. You are going to be given limited information. X of t is t cubed minus 3t squared. Throw a plus 2 on there for me. Throw a plus 2 on there for me. And it's not a particle, it's a dude. And the dude's moving on a straight line. Okay? And we're going to read all these questions and we're going to get intimidated. The average velocity. What's the velocity? What's the acceleration? It's like, oh man, I need all these formulas. But if you don't think about this unit and this lesson, Amber, switch table. If you don't think about this unit and this lesson as physics, if you think about this unit and this lesson as I've already done this, these questions are easy. Okay? So don't get out of your physics head right now and like watch me show you how this is stuff you've already done in this class. Okay, here we go. We're going to skip this first part. I don't want it to confuse you. We'll go straight to the easier parts. What's the velocity at 2? Oh, geez. I don't know. Well, Mr. Mester told me that the derivative of position is a velocity. How position's changing gives me velocity. I guess all I need to do is take the derivative of position and plug in 2. Could you take the derivative of position? Yeah, I could. I know how to take the derivative of t cubed minus 3t squared plus 2. It's 3t squared minus 6t. This is x prime. This is a velocity function. I didn't need a crazy formula to create it. You just take a derivative of position and you get a velocity. Could you plug 2 into that? I hope so. You get 0. Oh, what does that mean? Tell your neighbors, what does that mean if x prime, which equals v, is 0? Don't say, oh, it means the velocity is 0. No, what does that mean in terms of the dude moving on the line? Dude's not moving, right? If you have a derivative that equals 0, that means your original function must be like constant, neither increasing nor decreasing. It's like flattened out. If a derivative is 0, x must be constant. So a velocity of 0 means like you're not moving. X's position is not changing. The position of my dude is not changing. Okay, we'll skip average acceleration. We'll go to the acceleration at t equals 2. And if you get out of your physics brain, and instead stay in your calculus brain and say, well, like, I know v prime is a, and I know v prime is x double prime. All you realize is, oh, I just need a second derivative of the position function and I need to plug in 2. And you realize this is no big deal. Okay, so go ahead and do that for me. Don't check out. Don't be like, oh, this is a good lesson for me to sleep in, or pretend like I'm tired in. 6. V is 3t squared minus 6t. X double prime of t, which equals v prime of t, which equals a of t, is going to be 6t minus 6. X double prime of 2 is going to be 6. What does that tell me? Well, if a second derivative is positive, the first derivative is increasing. My velocity values are increasing. Okay? Why don't we skip this one and go to, when is the particle moving to the left? Talk about this for like 15 seconds. What would you do if I'm asking you, when is the particle moving to the left? No, this is like the perfect timing. Of course, it's like, oh, I'm going to ask you a question. It's like, oh, this is a great time for me to take a mental break. All right, listen, if you're still not jumping on this, ready? I'm going to show you how it's something we've already done. Particle moving to the left, I'm going to translate to my position is decreasing. I'm going to realize for my position to be decreasing, its derivative needs to be negative. Then I realize, oh, I just need a sign analysis of x prime, which is the same as v. We know how to do sign analysis. We find v, x prime, our first derivative, which is 3t squared minus 6t. We set it equal to 0. We factor to solve. 0 and 2 are the times when my velocity is 0. My velocity is 0 means that's when I've stopped. So I actually have figured out this answer right up here. We can do a sign analysis around these zeros to realize my position is increasing, then decreasing, then increasing. When am I moving to the left? When my position is decreasing, or when my velocity is negative, when t's are between 0 and 2. something we've already done. It just looks different. Okay? All right, your turn. When is the velocity decreasing? Let's see if you can figure this out. If you think this is a physics problem, translate it. It's not a physics problem. It's a calculus problem. It's a derivative problem. You know how to take derivatives. You know how to analyze derivatives. Go, figure it out. Everybody do it. Oh, who's taking mental breaks? Who doesn't want to handle this? Who wants to figure it out later? Who's checking out? Good. No, I don't know where you got -1. Oh, yes. Yeah. Who's giving themselves a shot here? And who's checking out? Who's like, yo, this looks different, so I like to take a mental vacation. How you guys doing over here? Mental vacationing, or are you going for it? Yeah, good job, guys. Good job. Good job. You should be proud of yourself, guys, if you're doing this. It's very easy to take mental vacation. It's very hard to think. Hopefully, you guys thought, all right, I need to know when velocity is decreasing. That's when velocity's derivative is negative. Hopefully you realize you need a sign analysis of your acceleration or the second derivative of position. We need a second derivative sign analysis. We've done a second derivative sign analysis before. The second derivative we found was 6t plus, or 6t minus 6. We set this equal to 0. We get 1. We get t equals 1. We do the signs. They're negative and positive. That means velocity is decreasing then increasing. When is velocity decreasing? For t is less than 1. Now, I don't know. Sometimes you'll be told time starts at 0. You can't have a negative time. Sometimes you won't. If you ever encounter a negative time, just think about it as like before somebody started the stopwatch, like in the past. Don't stress out about it, okay? We don't want to get into semantics of like, oh, can you have a negative time? It's like, sure, just go with it, okay? Do the question, you'll be fine. All right, next question. Is the particle moving toward the origin at t equals 1? All right, now, we've done all this work. To realize that just by given a position function, you can find a velocity function, and you can find an acceleration function. V is just a first derivative, A is just a second derivative. You may use 1, 2, maybe 3 of these to answer this question. Let's see if you guys can figure out which 1 or 2. Actually, you do have to use 2 of them. We'll just go with that. Which 2 of these do you have to use to answer this question? And what is the answer? Are you moving toward the origin, or are you moving away from the origin at t equals 1? Oh, I forgot to add a +2. Doesn't really make a difference. Does it make a difference? Yes, it makes a difference. We don't want it at 2. No, keep it as t cubed minus 3t squared. Now, here's one thing that we haven't actually done back in Unit 3. We never really plugged stuff into F. We didn't really care. We knew that F is going up, then down, then up, and we knew the concavity, but we never really cared about like y coordinates of F. We're like, let's have a little bit of fun and maybe just plug in some whole numbers. T equals 0, my position is 0. So I'm actually starting at the origin at the stopwatch. If I plug in 1, I get 1 minus 3, which is -2. If I plug in 2, I get 8 minus 12, which is -4. If I plug in 3, I get 27 minus 27, which is 0. If I plug in 4, I get 64 minus 16 times 3 is 48. 64 minus 48 is 16. Okay, now that actually helps me put a little context to this. My dude started at a position of, let's reset, at a position of 0. After 1 second, he's at position -2. After 2 seconds, he's at a position of -4. What happens then? Well, after 2 seconds, his position goes from decreasing to increasing. After 2 seconds, he changes direction. He stops. And he starts going back to the right. After 1 extra second, he's back to 0. And after another second, he's already at, where did he get to? 16, okay? Well, that kind of is understood by here. My velocity values start to increase. So I start to move faster, which is why, like, I go up 4, then I go all the way up 16. Since the dude was located at -2 and his position was decreasing, his velocity was negative. He's moving away. This is something a little bit new, towards or away from the origin, having to understand a position and a change of position. Okay? Cool. We're going to skip the position function. We're going to go straight to the velocity graph. Skip it a little bit. Go to something a couple pages later. Now, 3 questions. What I'm going to try to do is have you guys not think like a physics student, but think like a calculus student. Okay? Starting with, when is the particle moving to the left? This is the velocity. The first thing I'm going to do as a calculus student is realize, oh, this is just a derivative of position. Next thing, when is the particle moving to the left? Oh, my position is going to be decreasing. That's when the derivative is negative. Okay. X prime being negative, X is decreasing. I just need to look at when velocity is negative. Answer the question. Two to 4. when my derivative is negative. Oh, we've seen these before. These F prime graphs, where sometimes you got to look at when things are positive or negative. Sometimes you got to look at things that are increasing or decreasing. When is the particle stop? When my position is constant. My position is flattened out when its derivative is 0. Oh, that's when velocity is 0. The particle stops when my velocity is 0. When is the acceleration of the particle negative? If you're thinking about this in terms of physics, sure, you can get the right answer. I'll just show you how this is the exact same thing that we've done in the past in Unit 3. Acceleration negative. Acceleration being negative. Acceleration is the same as the derivative of velocity. If the derivative of velocity is negative, velocity must be decreasing. This is a second derivative sign chart analysis. The second derivative chart. Follow the charts. Okay, answer the question. Tell your neighbors what's the answer. Good. 1 to 3. My velocities are decreasing, which makes my acceleration negative. Okay? Now, we got to talk more about acceleration. We got to talk about speeding up and slowing down. Speed is the absolute value of velocity. It's velocity without direction. If your velocity was -3, you'd say your speed is +3. Now, going with your physics knowledge, tell me, when is something speeding up? Or tell your neighbors, when do you think something is speeding up? What's the answer to this question? Of course, that's what everybody would say. Something is speeding up when acceleration is positive, but I'm going to say, no, you're wrong. And I'm going to prove to you wrong by connecting this with some calculus. Okay? Here we go. If acceleration is positive, that means your velocity values must be increasing, right? And it's like, yeah, Mr. Messner, you're speeding up. Let me show you a set of velocity values that are increasing. -5 meters per second. Okay? Now it's a negative velocity. That means my position's decreasing at 5 meters per second. Ready? You want to increase from there? -4 meters per second. -5 to -4 is going up. To -3, to -2, to -1, to 0. Would you say these values are increasing? I would. Would you say somebody whose velocity is -5 to -4 to -3 to -2 to -1 to 0 is speeding up? No, I wouldn't. He is going left, but he's slowing down until he gets to a stop. So your preconceived notions about speeding up with acceleration being positive are wrong. Let me instead show you a different way to think about it. Speeding up is when the absolute value of velocity is increasing. Now, there's actually two situations when the absolute value of velocity is increasing. If your velocities are positive and increasing, yes, it makes sense. This means you are speeding up. You're going to the right and you're going faster to the right. Would you say these values are increasing? What about velocity values that are -1 to -2 to -3 to -4 to -5? Would you say that the absolute value of these velocities are increasing? Yes, because take the absolute value, boom, +1, +2, +3, +4, +5. Which means you got two options: positive and increasing, negative and decreasing. Gosh, that's so confusing this semester. I hate when we do like increasing rates, decreasing, negatives and increasing, positives and increasing. Mental breaks happen all the time. So instead, there's actually an easier way that we're going to talk about speeding up and slowing down. Instead of complicated calculus, ready? You're just going to watch. Look at the signs of velocity and acceleration. Okay? So, you see the arrows? If the arrows are pointing to the right, the sign is positive. If the arrow is pointing to the left, the sign is negative. Ready? We are speeding up going to the right. We're slowing down. We stop. We're speeding up. We're slowing down. Stop. Speeding up. Slowing down. Stop. Speeding up. Slowing down. Stop. Speeding up. What do you see about the arrows? And then he's gone. He's gone. Yo, if V and A are in the same direction, which means they have the same sign, this would occur. You're going to be speeding up. When V and A are going in opposite directions, which means opposite signs, you'll be slowing down. Speeding up is when acceleration's positive and velocity's positive, or acceleration's negative and velocity's negative. If your velocity's positive and increasing, or negative and decreasing. Okay, so back to like our original situation, I might ask you, when is the speed of the particle increasing? If you go straight to your acceleration sign chart, which you guys have done, and you're like, oh, when t's are greater than 1. Sorry, you're wrong. But if you combine your first derivative sign chart with your second derivative sign chart, you'll get it right. All right, there's your sign charts. You've already put these together. You did them, but now you guys answer the question. When is speed of the particle increasing? Student infinity is one of them. What's the intervals? You guys got the intervals? Yep, you got the intervals. When your velocity values are negative and decreasing, when your velocity values are positive and increasing, or when the signs of velocity and acceleration are the same. It's easier to go with that. 0 to 1, and 2 to infinity. Cool? Okay. Here's the graph of V. When is the speed decreasing? There are many different ways to do this. Go ahead. Don't take a mental break. Try. The more you understand now, the more you try now, the less you're going to do later, and the better you're going to do later. I don't like all of that, but I do like that. Oh, I love it, DJ Brown. Looking good. So many different ways to do this. Yes. Yes. Yes, Morales. Yes. You guys are doing so well. You're on the right page, Scott. They're rubbing off on you. Don't let them rub off on you. Benini's the worst person. Because Benini's like always like, oh, I never pay attention. But then you know that guy like works really hard and then he does really well on the test. So he's the closet hard worker at home, you know? He's like, I watch all the videos, but I never let in that I actually care. I'm going to pretend like I don't care, but so all of these? Not all of them. What do we get? Nice job. Did you think about that in terms of physics or, oh, I like what you're doing there? Yeah. Did you say I'm not in physics? All right, ready? Here's two different ways to do it. You can either create the full-on chart for V and V prime, which is A, or you can look for the specific situation when speed is decreasing. Okay? Now, speed is decreasing when velocity is positive and acceleration is negative. That's when velocity is positive and going down. It's also going to be decreasing when velocity is negative and acceleration is positive. So the signs are opposite. So you could say, I need to look at when velocity is positive but decreasing, or when velocity is negative but increasing. One way. Another way is to be like, yo, from 0 to 2, my velocity is positive. From 2 to 4, my velocity is negative. After 4, my velocity is positive. In terms of velocity's direction, it's going up until 1. It's going down until 3. It's going up after 3. Or the slopes are positive, then negative, and positive. And then from there, you can find your intervals. Here's one way to do it. The other way being, yo, positive and going down right there, negative and going up right there, or you can think about your absolute values. When are we getting closer to 0? When are we going 5, 4, 3, 2, 1, 0? We're getting closer to being stopped. -5, -4, -3, -2, -1, 0. When are we like slowing down to a stop? All of these are different ways. The last way being more of the physics way to get your answers 1 to 2 and 3 to 4. Okay? Now, if you just have, change this to a 6. Now, if you have a velocity graph, a velocity function, and you're asked about speeding up or slowing down at a point, you don't need a full sign chart analysis. You just need to figure out what is the sign of your velocity, what is the sign of your acceleration. Go ahead and figure that out. And then we have only 2 more problems to do, guys, and then we're done. I'll let you out early. But only if everybody actually tries. I know some people have been mentally breaking. It's not physics. This is just calculus in disguise. Not physics. This is just calculus in disguise. Ooh. Here, I'll give you the easy one. The velocity of pi over 9 is the sine of 6 pi over 9. The sine of 6 pi over 9 is the same as the sine of 2 pi over 3. The sine of 2 pi over 3 is positive root 3 over 2. That is a positive value. All right, so the velocity is positive. But now I need a sine. Oh, I don't know how to find a. I forgot. Can you give me a formula, Mr. Messner? No, you can give me the formula.
Slowing down. I literally wrote in the last question.
Come on.
I didn't know what to do. No.
What's the connection between velocity and acceleration? Okay. You're saying you can take the derivative of this and you're going to get this? Can you take the derivative of this for me? Okay. Thanks.
I did it with the 3P.
Okay. Cool. Cool. Z prime is cosine 6t times 6. V prime of pi over 9. If you're copying down, like, why even bother? Like, is that really going to help you when you're, like, doing anything? Copying down? Come on, guys. Cosine of 2 pi over 3 is negative 1/2. This ends up being negative 3. The velocity is positive. The acceleration is negative. That means my positive velocity values are decreasing. Positive values decreasing are getting closer to 0. We are slowing down. Or the signs of velocity and acceleration are opposite. All right, please go back to your position graph. Go back to your position graph. And then go to the bottom of that page. Here comes a challenge. Let's see if you guys are really taking mental breaks now. I'm even going to stand right here and make sure that it does it. Okay? Right here. This problem. Go. Okay. You can do it in your head. You're smart. Go, go, go. You guys want to get let out early? You can figure this out. Until Benini has the answer on his paper. We're not leaving. There you go. Use that red pen. Oh, you actually had a pencil. She found it. Cool. Nice, man. He's like, you always pan it. Pan. You like to pan. And then you're always paying attention. Good. Great. You got it. Keep going. You got it. Got. Yes. Rick, keep going. Well, here's how it goes, right? We started with position, and then we talked about position derivative and position second derivative. It's just like f prime, and f double prime. Okay, position derivative we said was what? That special word we use for it. Velocity, which means velocity's derivative has to be position second derivative, and we said velocity's derivative is acceleration. So if I'm given this middle row right here, and I want a position which is up here, what do I need to do? There we go.
Thank you.
Oh, you're not right.
Yes? Okay, because I think I did right.
You get it?
No, not really.
No. What? What? Good. 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 Yes. All right. Well, if all this is f prime, and f double prime, and they give me f prime, and they're asking me for f, I need to take an antiderivative. 1/3 TQ plus C. Yeah, we need a plus C. You were told x of 3 is 5, which means C is -4, which means we get 1/3 T cubed minus 4, which means after plugging in 2, we get 8/3 minus 12/3, which is -4/3. Oh, yeah, there's one more question I wanted you to do. All right, last question. What is the position of an object after 5 seconds given its acceleration at t is 2 and its initial velocity and position are 3 and 4? Everybody's like, ooh, initial velocity, initial position, I got to break out like vi or xi. No. Okay, and this is your first exposure to this word initial. Initial just means at time 0, right when you start the stopwatch. So if you're told initial velocity is 3, you are told v of 0 is 3. If you're told initial position is 4, you're told your x position at time 0 is 4. All right, now answer the question. Nobody's leaving until Scott has the right answer on his paper. Nobody's leaving until Benini and Scott and Paul Rock have the answers on their paper. Rick, don't give me the answer. Don't shut him.
I'm trying not to.
Don't shut him. They're cheaters. That's right. You just got to finish up. Good job, Rick.
Yeah.
Check it out.
And then you have to plug in the...
Yo, there is an equation. It's that x double prime equals 2. You got to go backwards and find C every step of the way. Don't copy it down. It won't help you. Just leave.
That was the hardest test ever.
Go. Get out of here. Yeah, why did you take physics, right? No.
It was just letting you know that I won't be here today.
Okay, thanks. Yep.
For retake, do I have to come in before school?
On B-Day.
You